Good day, ladies and gentlemen. This is our first discussion on physical science, grade 11, term 2. Today we are going to be talking about geometric optics, which is just a fancy way of saying how light moves. I'm using my glass pen, my glass dip pen, because during term 1 in my physical science class, I had a student who said I always have the strangest and most interesting pens. So I am making a point of using the strangest and fanciest pen I have today. Liema, if you are watching, this one is for you. Now, geometric optics is pretty much just a fancy way of saying how light moves. When we of course talk about light moving, you must know that the speed of light, which we abbreviate as c because it is the universal constant, is equal to 3 times 10 to the power 8 meters per second. Now, obviously, you're also aware of the fact that light is a form of electromagnetic radiation and that it is given off by objects like the sun, like a light bulb. This is nothing new. Now, you will also have, most likely in grade 8 to grade 9, seen the diagram where you have a flat surface and you have an object like a pencil or a candle, and then you have a light source. And what happens is, as the waves of light are moving, they will create an image. This image, of course, being shadow, and the shadow, of course, being larger than the original image because of the way the light moves. Now, this diagram is something you will have seen in a textbook in grade 8 or 9, but what I would like to draw your attention to is that when we draw light rays, they are always straight lines, obviously, and we use arrows to indicate the direction of movement. I'm not using a ruler at the moment, but if you have to, for whatever reason, draw a diagram, you need to obviously use a ruler. Now, light waves, being a form of electromagnetic radiation, carry energy. It is that principle of them carrying energy, being a form of radiation, that allows things like solar panels to work. And that also does bring us to our next topic, which is optical density. Now, optical density refers to how light moves through an object. Anything that allows light to move through it, air, water, a vacuum, is referred to as an optic or optical medium. And something that does not allow light to pass through it is called opaque. You might have heard of these words previously. In our example up here with the pencil causing shadow, the pencil being opaque, light does not move through it, hence it creates a shadow. Something that is 100% transparent will not create a shadow. Something which is 100% opaque will create a shadow. Now, I do not know if the camera is going to pick this up, but you can see that my pen is creating a shadow, even though if I put my hand beneath it, you can still see through it. That is because my pen is not 100% opaque, but it still creates a shadow. This is something that you do need to be aware of when moving forward, how materials that are opaque or optical media, how light interacts with them. We will talk more about that when it becomes more relevant, but for the moment, just please be aware of the fact that even subjects, or even objects, I apologize, even objects that are not 100% transparent, not 100% opaque, they can still have shadows. Another easy example is a glass of water. It does throw a very faint shadow. Now, optical density, as I said, refers to how light moves through something, how light moves through one of these optical media. If we use the example of a block of glass, the block of glass is made up of particles because everything is made up of particles, atoms, molecules, and such. Now, what happens when the light ray hits this optical medium? It energizes this particle. This particle carries the energy to the next one, and the next one, and the next one, and so on until it again exits the light block or glass block. Now, this principle of light moving through something is the crux of the optical density, and also brings us back to the speed of light, because objects with different optical densities will influence the speed of light. The way that light moves through the air versus a glass of water is going to be different, and we will talk about that in detail a little bit later on. Now, the topic I would like for us to cover today in a bit of detail is reflection. Now, reflection, as you certainly are aware, is when a light ray hits a surface and bounces back. A very easy everyday example of this is something like a mirror. So what happens is we have a surface. In my current example, a smooth surface. We have a light ray coming in. And of course, remember, we indicate the direction with our arrows. Now, the first thing that you need to consider when looking at something like this is the normal. The normal is a line perpendicular to the surface at the point where the light ray connects to the surface. So right here, perpendicular, that is our normal. The abbreviation for which being a capital N. Now, when we look at reflection, we have a rule. You have your incident ray, that is your ray coming in and hitting your smooth surface. It then gets reflected, it bounces back, and this ray that bounces back is your reflected ray. Now, the rule is that you have an angle right here from your normal to your incident and from your normal to your reflected ray. We'll call that theta of incident and theta of reflected. Your theta for incident is always going to be equal to your theta for reflected. You might have heard, perhaps if you've done something along this line before, that they say the angle of your incident ray is always equal to your reflected ray. And we can of course also measure this angle and this angle. They will always be equal to each other. Now, this is relatively important because this is not just, well, it's the rule for reflection, but this rule is important because it allows things like mirrors and other optical instruments that we use to function the way that they do. If we use the example of a mirror now, we have a smooth surface and we have our incident rays. I'm going to simply label them as I for incident. Now each of these we also have a normal. I'm not going to be labeling those just to keep the sketch a little bit simpler. And now the incident and reflected angle will always be the same. So what we see is if you have light rays parallel to each other, being reflected from a smooth surface, the reflected rays will still be parallel to each other. This is pretty much how a mirror works, and we will have a sketch of that in a moment. The other important thing for reflection is, of course, if we have a rough surface. Let me just do that. Now if we again have our incident rays coming in, and they are again coming in parallel, now we make our normals, and you might notice that when they are reflected, they are no longer parallel to each other. So the largest difference between a smooth and a rough surface is that your incident rays are all parallel, your reflected rays are all parallel. On a rough surface, your incident rays are parallel, your reflected rays are not parallel. Now, this is something that you might have encountered in grade 9 or grade 10 science perhaps, but regardless, this is what you need to know about reflection. The only other thing that is important at this point about reflection is exactly how a mirror works. Now, a mirror follows certain rules. If we say that this line over here is our mirror, and that right here we have an eye which indicates the observer. Now if we have our object over here, what happens is light is coming off of this object and it is hitting the mirror. Now we have our normals, of course, and these rays are then reflected, and obviously we are able to see them. But what happens is the way that our eyes works, it means that we are actually seeing a bit of a illusion. You might notice if you look at a mirror that it almost looks as you are behind the mirror. This is the way that light moves, and that causes that effect to happen. What happens is the object, light gets reflected from it, that reflected light is perceived. The way that our brain perceives light and the way that light behaves makes us want to think that these light rays are moving in a straight line. So the object appears to be the same distance behind the mirror as it is in front of the mirror. This being, of course, the image that we see. Now, there are a few rules when looking at mirrors. The first one being that the object and the image are the same size. The distance between them is equal to each other, the distance that we perceive them. The image is laterally inverted, left and right side are switched. You may have also noticed this. It is always upright, right way up. It is a virtual image. We realize that this is not a real object that we're actually looking at. It is a virtual image of the real object. And that is pretty much how mirrors work. Now, this diagram over here, in essence, summarizes your principles of reflection. This diagram, together with the smooth and rough surface diagrams, is pretty much everything that you need to know at this point about reflection. For our next discussion, we are going to have a little chat about refraction, at which point the concept of an optical media will again become important. Until then, have a good day.